Okay, so the Foucaults pendulum, often used to prove the spin of the Earth on its axis, and the premise is that you suspend a pendulum that's free to spin in any direction, and you set it off swinging, and the spin of the Earth below the pendulum is measured on some sort of measuring device, in this case a compass, and from an observer it appears over a certain time period, dependent upon where you are on the Earth, the pendulum seems to be moving around, in this case at the North Pole, clockwise. If we now traverse to the South Pole, you'll see that the opposite happens, and it indeed goes anti-clockwise. If you were to set one at the equator, then the swinging motion of the pendulum would indefinitely remain aligned, since it is always going to be the same with respect to the spin of the Earth on its axis. An extremely important requirement for the pendulum to be effective is for the bob to be as massive as possible. They're usually lead with brass coating to make them extremely heavy. You'd struggle to pick one of these things up. So the more massive the object, or the bob, the better the pendulum effect will be. So in order for the pendulum to work effectively, it requires a really tall building to suspend it from. Typically 15 metres upwards is ideal, but the longer the better. And they do appear to exist in the northern and in the southern hemisphere, and they do indeed, by all accounts, spin anti-clockwise in the southern hemisphere and clockwise in the northern hemisphere. It's pretty difficult to or time consuming to actually verify this, because you'd have to be stood there for hours on end to see any meaningful change, but I've got no reason to doubt they work, and they're said to work using the Coriolis effect, or the Coriolis effect acts upon them. So these were first publicly demonstrated in February of 1851 in the Paris Observatory. So let's start in Paris, and we'll draw a yellow line up to the North Pole, and the red line represents the rotational direction of the Earth to the east. We'll put on there the pendulum, a much larger pendulum, and the two balls, the orange balls, represent the extremities of the swing of the pendulum. Notice they are aligned with the north, so as the Earth rotates to the east, the pendulum wants to stay in the direction that it was originally swung, and the North Pole is still pointing north. So if you measure the angular difference between the first point and the second point, shown in green, you'll find that the angular speed is proportional to the sign of the latitude. Meaning if you were kidnapped and flown to a secret location and put in a room with only a Foucaults pendulum, a clock and a calculator, you should be able to determine exactly the latitude that you're at on the Earth. Now some Foucault pendulums, like the one in this picture, they have the 4 cardinal points marked on them, and some have the individual degrees, the 360 degrees in between as well. My point being that the effects of the Foucault pendulum aren't just confined to the room that the pendulum's within. For instance, that north line there will extend out of the room and continue all the way to the North Pole, and at any given point along that line, the exact same principles that are occurring within the room the pendulum is in itself is occurring along that entire line, albeit at varying different angular velocities depending on your latitude. Logically then, if we were to scale this Foucault pendulum up and set it over France, so we're travelling from southern France to northern France, a distance of about 500 miles, travelling due north. Let's say that we scale the bob up to the size of a bus, and we sit in the bus, and we are travelling at a velocity of 500 miles an hour. So we're going 500 miles and travelling 500 miles an hour, so it'll take an hour. Now, assuming the pendulum was released from the south so that it is travelling exactly north, after 1 hour, will we still be travelling north? Or will we be travelling northeast, as the Foucaults Pendulum would dictate? Well, according to the maths, at a latitude of 50 degrees in northern France, we should have rotated by about 11.5 degrees to the east in our giant swinging pendulum. After all, during the swing of the pendulum, it just wants to go in the direction it was originally swung. It's not until you reach the end of the swing at either end that the eastward motion of the Earth will kind of tug on the pendulum and cause it to move across the Earth. And since we're only talking about one large swing for the entire 500 miles, then this tugging action to cause it to move eastward would not occur. So if we now gave the bus some wings and some engines and cut the wire, would it behave in the same way? Well, no, it wouldn't. It doesn't. It's not what we see. We don't have to make any sort of correctional track changes to account for the plane's tendency to want to go in the same direction as it was originally launched. So let's piece together and paraphrase exactly what's being claimed by science for the explanation of the Foucaults pendulum. So what they're saying is a mass, the more massive the better, moving at velocity above the Earth but independent from the Earth, will tend to continue on the same trajectory with respect to space, not with respect to the Earth. Let's look at a visual representation of what's being claimed. So what I've got here is a pendulum. I've suspended it from as high as I can get with my tripod. And there's a bob on the bottom, and I've fixed it to this platform that rotates. So I just want to show the effect of the Foucaults pendulum. So this would represent your destination, i.e. northern France. Let's say that's southern France. And let's set the pendulum off going straight as we can, and in one swing I'm going to rotate this platform very slightly to show the effect. So here we go. So it's moved, apparently the destination's moved left, and this pendulum is still swinging in the original direction that it was launched from. So that would be the 11.5 degree difference we calculated earlier. So I want to just point out that this motion here, that the fact that it appears to spin on the spot, it's not through any external force what is proposed. This is just purely where it wants to go. No force is being applied anywhere. The Coriolis effect is exactly that, an effect. The Coriolis acts on nothing. It's just an outcome, a visual outcome of what happens when an object moving at a velocity across another rotating object. That's all it is. So the Coriolis is just an effect. It's acting on nothing. There's nothing, no force acting to make it go in that, to make it spin. So what I want to know is, what is different about this mass than any other mass on this planet? What is it that's different about a pendulum that differs from a plane? If this was an aeroplane, if we go back and say that's the destination, This is an aeroplane. The aeroplane does this. The Foucaults pendulum does this. Why? What's different about this mass to an aeroplane? Well, I have my own theory on the matter, and I believe that there is no difference. In that initial first swing, there is absolutely no difference between an aeroplane and a pendulum, or any mass for that matter. It's my belief that the difference is that a pendulum is an oscillating object, and at the end point of the swing, when it reaches its extremity and it turns to come back, that's where I believe the spinning effect is coming from. Remember, there are vortexes, spinning vortexes everywhere in nature. In fact, magnetism is, by definition, a vortex. So the reason that an aeroplane doesn't behave the same way as a pendulum is that A, it's moving in a linear direction, there's no oscillating component to it, and B, the Earth isn't spinning. Then when you consider things like the Allais effect, which is the anomalous behaviour of pendulums during a solar eclipse, which some people claim to have witnessed, you start to think that perhaps this is a magnetic effect. Perhaps the solar eclipse creates some sort of electromagnetic disturbance. Unfortunately for me, however, being in the UK, we're not expecting another total solar eclipse until the year 2090, and the next deep partial eclipse won't be till 2026. That, and I haven't got a Foucaults pendulum, kind of prevents me from testing this phenomenon. But I am still testing my gyroscopes. If you watch my rigidity in space video, you'll see why, and why the gyroscope appears to behave very, very similar to a Foucault pendulum, in that it wants to remain rigid in the same orientation as it was originally spun up. So, I hope you enjoyed the video. Look out for the results of my gyro experiment, and thanks for watching.